Good embeddings are not just about the loss. The projection head changes where learning pressure lands, so the final embedding space can come out cleaner. This is the workflow you'll know how to run when we're done, which trains a projection head on labeled pairs and measures separation while keeping the base representation clean. I'm Professor Pi, teaching AI foundations with simple Python. Embedding projection heads solve a common problem. You often start from a pre-trained encoder that already knows language or images. You only have a small labeled set for a specific task. If you fine-tune the whole encoder, you risk destroying the general structure you care about. A projection head lets you train a small, cheap layer where the contrastive objective acts, while the base encoder stays stable. Success looks like stronger nearest neighbor separation in the head, with the encoder preserved for reuse. At a high level, a projection head is a shallow network placed on top of your encoder. You use it to create a space where positives and negatives separate under a contrastive objective. The head is cheap to train and reversible if you want to inspect the base embeddings. The trade-off is that a head can hide signal changes from the base unless you choose to propagate gradients. We will build a tiny experiment that shows 3 behaviors. First, we will measure base similarity with an untrained encoder. Then, we will add a projection head and inspect a contrastive loss. Next, we will compare retrieval in base and head spaces. After that, we will train only the head. And finally, we will train both head and encoder together. This keeps the code minimal and the lessons direct before we run anything. Now we will build a tiny encoder and check baseline similarity. This snippet builds a tiny PyTorch encoder and measures cosine similarity between 2 items. We seed randomness for repeatability, then create simple clusterable inputs by selecting rows from an identity matrix and adding small noise with torch.nn. The NN linear layer, named enc, projects 5-dimensional inputs into a 4-dimensional embedding, and fnormalize keeps vector lengths comparable. We compute Z as the normalized base embedding and use F cosine similarity to quantify how aligned the first 2 samples are. Because weights are untrained, this score reflects a weak baseline representation. The printed cosine shows how similar a same class pair appears before any projection head or training. Next, we will add a small head and compute a contrastive loss. This example adds a projection head in PyTorch and computes a contrastive loss value. We reuse C from the encoder, then define head as a small NN sequential with ReLU and a linear layer to shape the space where we train. The variable H holds normalized head outputs, and H matrix multiply H transpose builds pairwise similarities. We scale by tau and call logits fill diagonal to ignore each item comparing to itself. The tensor pos maps each sample to its positive partner, and F cross entropy turns the similarity matrix into a softmax classification objective. Lowering tau sharpens comparisons and often increases gradients. Raising tau smooths them. The printed loss quantifies how well positives outrank others with the head. Now we will compare nearest neighbors between base and head spaces. This snippet compares nearest neighbors from base and projection head embeddings in PyTorch. We compute C from the encoder and H from the head, normalizing both with fnormalize so cosine comparisons are fair. The expression Z matrix multiply Z0 scores similarities to item 0 in the base space, and torch top K retrieves the best match after skipping the trivial self-match. We repeat the process for the head space and then test whether the 2 top 1 neighbors agree. This highlights how retrieval can differ when training acts in the head. The printed Boolean reveals whether both spaces currently pick the same nearest neighbor. Next, we will train only the projection head while freezing the encoder. This example trains only the projection head with a temperature parameter. We freeze the encoder so its base space stays clean. Then set an SGD optimizer on head to make training focused and quick. We record S0, the initial cosine of a positive pair, and iterate short updates where logits come from the head space, scaled by tau. The call logits fill diagonal removes self-comparisons, and F cross entropy encourages each sample to rank its positive partner highest. Lower tau sharpens peaks and typically speeds separation. Higher tau relaxes pressure, but may require more steps. The printed gain shows the head-pulled positives closer without touching the encoder. Now, we will jointly train encoder and head, and then evaluate base retrieval. This snippet jointly trains encoder and head, keeping base embeddings for use. We optimize both parameter sets with Torch Optim SGD, but still apply the contrastive objective only in the head space. Each step refreshes Z from the encoder, computes head activations H, forms temperature-scaled logits, and ignores self-similarity with logits fill diagonal. The loss from F cross-entropy flows back through the head and into the encoder, gradually improving the base space too. After training, we evaluate downstream by retrieving the nearest neighbor using only Z. The printed ID shows which item is most similar in the cleaner base embedding space. In a real project, this toy setup maps directly. Replace the identity-based toy inputs with your real samples and label pairs. The same pattern lets you try head-only updates quickly, then decide if encoder updates are worth the cost. Recap. What it is. A projection head is a small network added on top of an encoder to host your contrastive objective. When to use it. Use it when you want fast, task-specific separation without corrupting a pre-trained base. One caveat. If you need the base itself to change for downstream tasks, training only the head will not be enough. Next step. Tune the temperature parameter tau and observe how sharpness changes learning speed and final separation in both head and base spaces. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.